Thank you everybody for joining us today, and I will be presenting our new large field of view Raman Spectroscopy kit that is going to be added to the THORLABS catalog soon. If you have any questions during the presentation, feel free to type them in the chat. So first of all, let's look at Raman Spectroscopy. What this technique does is it provides a chemical fingerprint of your sample, and this enables you to quantitatively analyze any chemical mixture. This can be used, for example, to identify illegal or dangerous substances, or for quality inspection. If you think of pharmaceuticals, food, beverages, and many more items, this can be very useful. You can also use this for live monitoring of chemical processes at production sites. The main advantages of Raman spectroscopy is that there is no sample preparation required. So this technique is non-destructive and also non-invasive. You can even detect samples through transparent packaging, like glass or polymer. Raman spectroscopy is also well suited for water-containing samples, as this technique is not very sensitive to water. Usually, you can get a decent spectrum in a few seconds measurement time. Let's take a look at a typical Raman spectroscopy setup. So you start with your laser, and then you irradiate your sample. The laser light is then scattered at the sample, and you can analyze the light in a spectrograph. So you focus the light onto the entrance slit here, then you recollimate the light onto a grating, which separates the different wavelengths, and those are then detected at your sensor. And what you will find when you do this analysis is that the scattered light has different wavelengths than the initial excitation beam. Because what happens is you excite your molecules to a virtual state, and then it relaxes to an excited vibrational state. And the difference in the initial photon energy and the scattered photon energy is called the Raman shift, and is exactly the vibrational energy that is left in the molecule. So, for example, in the lower wave number region, you will often see spectra like this. This is very distinct and also called a fingerprint region because of that. And in the higher wave number regions, you will usually find terminal atom vibrations like CH groups, OH groups, or something like that. To get decent Raman spectra, you usually need a high spectral resolution, somewhere between 5 and 20 centimeters to the -1. And the general rule is the smaller your entrance slit of your spectrograph, the better your spectral resolution. So typically you will see slit sizes of 25 microns and less. What this means is that you lose a large amount of light intensity at this slit, and you need to compensate for that. You have several ways to do that, and typically what you see is that expensive cooled CCD sensors are used, long measurement times for averaging, or high power lasers are focused onto very small spots here to increase the scattering from the sample. What this in turn means is that the highly focused laser beam only allows you to analyze a very small field of view of your sample at the same time. What our spectrograph does is a bit different. So here you see a standard aperture size with those 25 microns. And this is our aperture, which is very large, 2.3 by 3.2 millimeters. And usually such a large aperture would cost you a lot of spectral resolution. We make up for that by using this mask inside the aperture. So the pattern here is not random, it's actually a Hadamard mask. And we can use that to deconvolute the images from our sensor to reconstruct a spectrum with a high spectral resolution between 7.8 and 9.7 centimeters to the -1, despite this large aperture. And what we gain by doing that is a lot of light in our spectrograph. This allows us, for example, to use more cost-effective components like a room temperature CMOS camera instead of a cooled CCD sensor. What it also does is it increases our sampling beam. So usually you have a few microns beam diameters for sampling, and we have a 2 square millimeters field of view, which is a lot larger. And what this automatically does is integrated averaging over a large area. So if you're interested in the average composition of a sample, you can obtain that a lot faster and easier with our spectrograph. Also, this lowers the laser power density that is incident on your sample, which is a lot safer and less harmful to delicate samples. So now let's take a look at the spectrograph itself. So here's the aperture, here are the optics, and then we have the camera sensor here. This comes wavelength calibrated and also amplitude corrected. So this allows for a direct comparison of any recorded spectra with spectral databases. You can use 2 different excitation lasers. The first one is 785 nanometers, and the second one would be 680. If we look at the most important specifications, you can see that the aperture, again, is extremely large. The numerical aperture is 0.22. Spectral resolution varies between 7.8 and 9.7 centimeter to the -1. And with the 785 nanometer laser, you can reach the fingerprint region between 500 and 1800 centimeter to the -1. Also, if you switch to 680 nanometer excitation, you can access the terminal atom vibrations between 2000 and 3600 centimeter to the -1. At very short measurement times of about 10 seconds, you usually reach a signal-to-noise ratio of 700 or better. Our amplitude correction, which enables you to directly compare to any databases, follows the NIST standard SRM 2241. In addition to the spectrograph, we also offer all the necessary accessories to get started instantly. So we have two different front ends. First of all, this reflective one for solid samples here, and the cuvette holder front end for liquid samples here on the right. These are designed for fiber-coupled lasers, so you basically just need to connect your fiber-coupled laser pigtail, and then you can place your sample, for example, here on the sample table or inside this cuvette, and then you can start your measurements instantly. They also come with laser calibration wavelength standards, so you can check your laser wavelength whenever you like. The modular design of all these front ends is also compatible with all of our standard THORLABS optomechanics, so you can easily customize your setup. For example, by adding polarization-dependent optics for polarization-dependent Raman spectroscopy, if you like. To talk about pricing, the spectrograph is going to be available for $13,000 US. The reflective front end will cost around $4,400, and the cuvette front end will be available for $3,500 US. Yes, to just quickly summarize, we use the patented large-coded aperture technique to increase the light throughput and achieve a higher spectral resolution at the same time in our Raman spectrograph. The beam has a very large area, which in turn results in a very low power density at the sampling spot. So you get integrated averaging, and you can obtain the composition of samples very fast and very easily. And it also allows you to analyze delicate samples because the lower power density is a lot less harmful to them. You get your spectra in a few seconds usually, and we have all the accessories available to get started instantly. The kit is also modular, so it is compatible with all our standard THORLABS optomechanics, so you can easily customize and adapt the setup to your individual needs. And with that, I'd like to thank you all for coming today. And if you have any questions, feel free to type them in the chat.